Hello again. Now we're looking at multiple linear regression. So this is similar to simple, except the problem here is we've got more than one variable. So as before, we need to understand the concept of multiple linear regression, analyze data in R, interpret the results of the analysis, also use categorical variables in regression, explain how that works and what the meaning of the result of the output is. Perform diagnostics as before, and then determine any transformation of data. And this is what we'll be looking at afterwards. And then evaluate models as before. So here the idea is exactly the same as before. We won't spend time trying to work out the parameter values in this case. We'll simply use R for all the calculations. So we'll still fit the regression model, we'll perform diagnostics, we'll take a look at some ideas of what I'm going to call here non-linear regression, and we're going to start building models. So if I've got some data, how do I find the best model? Then we're going to include also categorical variables, and finally look at ideas of data transformation when the problem arises with some of the model diagnostics. In summary, so all the data in this available in this file, in the Excel file, which you can use to play with yourself. So here was the FarmX in detail. We had looked at all this before. And then have a table, no problems at all. Now the R squared, in this case, R squared was the regression sum of squares over total sum of squares. Multiple R was R, the square root of that. Now, what we look at is what's called the adjusted R squared in this case. The multiple R version is exactly the same. We have regression sum of squares over total, and so this works in the same way. Now, so R squared also is 1 minus sum of squares of regression over sum of squares of total. What you'll find here is that the calculations here, as I say, will be the same as before, except R will read all of this for us. This example over here is the price of beef. This is the data on the price of beef. We've got the year, we've got PBE is the response variable, the price of beef in cents per pound, this is English data, and we've got various indices over here, consumption of beef index, retail food index, and so on, disposable income, and so on. There are other variables in here. We'll try and regress this. We want an equation here that looks like this. Price of beef is beta naught, the intercept, plus beta 1 times the first, and so on, all the other things. And here is the random error term. So we're going to see how this model fits. So the first thing we do is, here's the data, and you can have a look at this. It's available on LMS. And analysis in R is simple. We put the model equation, model data in there and model it. Here is the output from R. The important thing is we focus on those variables that are significant. So those two and this last one here. At the moment the intercept is there. The CBE, the consumption of beef per capita, whatever. And here this is the CFO, some of the index as well. Those are the only significant things. The rest of the terms in the model aren't significant. How do we proceed from here? Well, we take a look at the p-values. We take a look at we can do the test here separately. So here the test, if I list them all, I've got the null hypothesis as beta not equal to 0 versus beta 1 against beta 1 not equal to 0. The p-value is very small, so I reject H naught, and I've got the whole log listed here. So those are the three where I reject H naught. Those three are the significant terms in the model, and the rest of the terms in the model are not significant. How do we proceed? Now, having said all this, in general, we won't ever list this again. We'll simply look at the p-values from the output of R and from there select the significant variables. So far the model equation is simply this. Now, how do you know if this is the best model, and how do you proceed from here to find the best model? And the final model should include only significant variables. So what we do here is we remove non-significant variables from the model. But here the problem is that multiple regression behaves very differently to simple linear regression. That only consists of one variable. Here there's several variables. We remove variables one at a time, refit the model, and then we look again to see what is significant, and then remove another variable if there are some insignificant ones here. Now, multiple regression is very tricky. Sometimes removing one variable or putting another one in can change the significances of the other variables in the model. General advice is some experimentation is required. You put a variable in, take one out, and so on to see what's going on here, and such fitting will give you some insight into the behavior of the model. So here, those variables are not significant. We pick the one with the largest and drop that. And so when we do that, we will find that some of the coefficients will change. And so we drop the largest, the variable with the largest p-value, refit, the coefficients will change, but then what we do is we look at this again. So here, we fitted the model without RFP. Now, interestingly, once I've done that, once I've dropped that one variable, you see everything is now significant. Now, that's interesting. So just one variable out, and the model now contains only significant variables. So yes, now all the variables are significant. Multiple R is almost the same. Adjusted R squared has increased. So if you look at the values here, adjusted R squared 0.9433, and previously it was 0.9416. So there's been some change there. So what's this adjusted R squared? The R square value does not adjust for the number of variables in the model. If you add another variable, R squared will not decrease. It may increase, maybe not by much, but it won't decrease. But a simpler model with fewer variables is to be preferred over more complex. For many reasons, prediction is easier, control is easier, understanding the structure is also easier. So just as R squared, actually, R squared as it stands is 1 minus residual sum of squares over total sum of squares. What adjusted R squared does is it takes a look at the mean sum of squares of residuals against the mean sum of squares of total. So it actually adjusts for the number of variables. You can see there's n minus k over here. The fewer variables, the larger the top is going to be. So here for this, the adjusted R squared is 1 minus, if I look at the sums of squares that I've calculated from somewhere else, you look at the neighbor table if you wish, then I get 0.9433 here. And this sum of squares actually have been obtained from the neighbor table. Well, how do we select a better model? We're going to use all of these larger value of multiple R squared. We'll take a look at the adjusted R squared as well. And we'll also look at a smaller standard error. Smaller standard error is indicator of a better fit of the model. Diagnostics as before. As for the simple linear regression, exactly the same as before. Normal probability plot for the probability normality assumption, histogram of the residuals, also for normality assumption. Here you find that this is not so different from straight line. It's not very far, it's some queerness over here, but it doesn't really matter. But that combined with the histogram looks okay. If I look at the standardized residuals against the fitted values, nothing here is outside the -2 bound, no serious change of spread, and so that's all right. Now, often what we have though is the relationship between response and explanatory is not straight line. It could be something else. How do we work it out? Well, the scatter plot can be a guidance as well, but the more important guidance is going to be looking at some other plots we'll see afterwards. So common functions over here. This is the square function, and this inverse the square root. This is the exponential function, e to the x, and it's inverse of the log function. Now, the big part here is building regression models, and we'll see that in the next lecture.